Hello to all. I'm Abolfazl Simorgh, a third-year PhD student under the supervision of Professor Manuel Soler. Today I'm going to present my research progress during the last academic year, which is about robust climate-optimal aircraft trajectory planning. As you all know, aviation is contributing to global warming through the emission of CO2 and other non-CO2 climate effects, including formation of persistent contrails and NOx-induced changes in atmospheric concentration of ozone and methane. Considering the strong growth rate of aviation industry, a critical increasing its associated climate effects is expected, so we need to move toward greener aviation. A question arises here: how can we mitigate the non-CO2 climate? How can we mitigate the aviation-induced climate effects? In fact, the non-CO2 climate effect, which is responsible for 2/3 of aviation effective radiative forcing, directly relies on atmospheric condition at time and location of emission. So there are some areas of airspace with less sensitivity to aircraft emission in terms of climate impact. By identifying such areas, we can include it in flight planning tools to reduce their impact. To generate a coefficient flight plans, we need to first identify climate-sensitive areas. There are two approaches in the literature to a state-of-the-art approach. One of them is the algorithmic climate change function, which take as input a specific meteorological variables such as temperature, geopotential, and estimate the climate effects in terms of average temperature response for a specific species such as contrails, NOx emission, water vapor emission. And the other one is called COSIP, which also take as input specific meteorological variables, but here we only estimate the climate impact for contrails in terms of energy forcing. So as mentioned, these two models take as input meteorological variables. So as we all know, weather forecast is never exact, and this can bias the estimation of climate-sensitive regions. So in this study, we take as input the ensemble weather prediction system, which provides n different possibilities for weather condition in the flight planning to consider the uncertainty in meteorology and also resulting climate-sensitive areas. As also mentioned, we now, for example, have two methods to estimate climate impact. So, for example, for contrails, COSIP and algorithmic climate change function. We also tend to provide robust trajectories with respect to these two models. So not only meteorological uncertainty, but uncertainty associated with climate models. About the state of the art, we already conducted a survey on recent studies in this field and identified four main gaps. The first two, which is related to considering uncertainty in flight planning and efficient trajectory optimization solvers, will be addressed in my thesis, but the rest two, network scale trajectory planning and also new models for hydrogen and hybrid vehicles, will be addressed by Fatima and Raul in the next two presentations. So, about our progress during the last year, I start with climate optimal flight planning, considering weather-induced uncertainty. So I show the concept with an example. For identifying where persistent contrails are formed, we mainly need two atmospheric variables. One of them is temperature and relative humidity. Now we can see two different forecasts or two different members of an ensemble prediction system. We can see a significant difference between relative humidity fields, and this leads to identifying two possibilities for contrails formation. So if we include, for example, one of them in the flight planning and solve deterministic optimization, we may lose the mitigation potential. So the best approach is to consider all possibilities, which is characterized using ensemble prediction system to determine robust trajectories. So in this respect, we already solved this problem for the structural space, which was presented last year. But to increase the efficiency of the air traffic management system, we need to move toward free routing operations, which allows us to plan trajectory more flexible. So here we are using different approaches to solve climate optimal trajectory planning under weather-induced uncertainty. And here is the problem formulation and optimization approach. I'm not going to present all, but basically we use a robust tracking optimal control problem framework to model this trajectory planning problem. And we discretize uncertainty and convert robust formulation to deterministic flight planning problem, which is then solved using direct optimal control approach. Here is some results. Is for a flight from Frankfurt to Kiev on 20th of December 2018. We use algorithmic climate change functions to model climate effects, and using ERA 5 data products, including 10 ensemble members to characterize weather uncertainty. And the objective function is expected SOC. SOC means simple operating cost and is to represent operational cost. And expected ATR, which is weighted by EI. ATR is average temperature response, and EI is a weighting parameter that we change to identify alternative solution. Here we can see that, so EI equals 0. We see that this cost optimal trajectory, it flies at higher altitudes, which is beneficial for fuel consumption. But as we penalize average temperature response with higher weights, for example, the yellow one, we are flying at lower altitudes. And if you look at the climate response, it's the climate average temperature response of contrails, NOx emission, water vapor, and net. We first see that it is dominated by contrails if you look at the net and contrails. And we see that by reducing altitude, we are mitigating the climate impact. And to justify that, it flies at altitude 9 kilometers here. And if you look at, so the color bar shows the ACCF of contrails, the blue area shows cooling impact, and the red one shows warming impact. And we can see that the yellow one deviates from shortest path to maximize generating cooling contrails. Contrails during daytime reflect incoming solar radiation and may lead to cooling impact. So, but we can see that in the results, we have uncertainty. The shaded ranges shows uncertainty. And we can see we have uncertainty. Now, let's see how can we reduce the uncertainty ranges. Here we have a figure to reduce uncertainty. We add a term, which is called, variance of average temperature response, and we have weighting parameter there. So, we take the best climate optimal routing option in the previous slide, which is 50, penalized with 50, and now add penalty on the dispersion of climate effects. We can see that all of them again flies at this altitude because it was beneficial for generating cooling contrails. But the yellow one, which we penalize with 5, I don't know why the quality is reduced, but we are avoiding areas with high standard deviation of contrails. So high variability among the estimations. So this is the standard deviation of contrails. And we can see that if you look at the yellow one, the uncertainty is reduced. So by avoiding areas with high variability. And here is the Pareto frontier, and it's good for analyzing alternative solution and efficient decision making. So the next one is the concept of climate optimal flight planning under multiple estimations. So during my stay at TU Delft, I was working with another model for quantifying climate effects. And I observed that sometimes there is a strong mismatch between the estimations. For example, here we can see that these two maps are supposed to be similar, but not. So this motivated us to introduce a concept, flight planning under multiple estimations. So basically here we try to optimize trajectories such that areas of airspace that we have good agreement with estimations to fly there. So this is the main the topic of this one. So about the formulation, here we consider as input n different climate models. Each model can be represented with its own weather data, emission calculation model, and also assumption. And we formulated similar to what we had for meteorological uncertainty. And if I want to show a case study here, we have another flight. Here we explore 3 different routing options. One of them is the cost optimal trajectory. The other one is climate optimal trajectory, focuses on one model. And the other one is robust trajectory planning. Here we have 2 different models. Model 1 is, we call it IMAC, is from climate chemistry model. And the other one is climate SCC with era interim weather data. We see strong differences between estimations. So if we look at the cost optimal one, we can see that the climate effects are almost consistent. For example, the yellow one is NOx emission, the light blue one is water vapor. But if you optimize considering model 1, only one of the models, we see that for model 1, we are increasing cooling contrails. So we are generating cooling contrails here. But if you assess this routing option with another model, model 2, we see that we are generating warming contrails. So it should be critically taken into account. Okay. So, and to justify the reason, look at this altitude. Here, the red one flies in an area to maximize cooling contrails, but here, if we look at this altitude, we see that it generates warming for the other one. But if we use our proposed methodology, it's possible to have mitigation potential and also consistent estimations. And yeah, we also use this approach for 2 other models, the COSIP that I presented earlier, and also we consider meteorological uncertainty. So meteorological uncertainty and uncertainty associated with estimation, and it works successfully. And yeah, we aim to explore it more. And about outcomes of my PhD so far, I have almost 2 papers published and 2 hopefully submitted by end of this month. And I attended several conferences to present different parts of my thesis. And about next steps, now, okay, it's the last slide. Okay, basically now we have access to state-of-the-art climate estimation models. We have the tools ready, and we have the approaches to consider different aspects of robustness. So we want to apply our methodology and analyze simulations over 1 year to find, for example, which weather patterns are suitable for flight planning. For example, during December, it's better to, for example, use climate optimal planning, but for specific months or weather patterns, it's better to stick to business as usual trajectories. So we want to perform this analysis and hopefully publishing in Nature. And the last step is writing thesis, so which I want to do. I have to do, but I'm not happy with that. Okay, thank you very much for your attention. Thank you.